It's time for our next plenary speaker. Can everybody come in and get their seats, please? So I'm actually greatly honored to introduce our next speaker here, Tyler Erickson from Google. Dr. Erickson is a developer advocate and he's been working on geospatial analysis platforms, the Earth Engine. About a couple months ago, mid-March, he was invited to the White House to present the Earth Engine and related to climate change. So he's a pretty busy person, and I've had a few emails exchanged with him in the last couple of weeks, but we are very grateful that he's here today. And on behalf of the organizing committee and the Delta Science Program, I want to invite and thank Dr. Erickson here.
All right. Thank you, George. So I guess for the presentation, we'd have to get it into the present mode. Awesome. Thank you. So thank you for the introduction, George. And I'm going to talk to you today about some of the tools that Google has in terms of geospatial data in the context of California environmental data and broader environmental data. And I tried to specifically pull some examples for water resources, figuring to be of interest to this crowd. But main thing I'm going to talk about is Earth Engine of our technologies, and it is a cloud-based geospatial analysis platform. I'll go into a bit of detail throughout this presentation on what that actually means, but just to frame the context of it, it's basically you can do a lot of remote sensing and GIS-type operations in the cloud, so not installing your own software, but you upload it into the cloud and operate on it there. I have the role of what is known as a developer advocate at Google. And what that really means is that I stand in between our tools on the inside, particularly Earth Engine, and scientists, developers, people on the outside that are trying to make use of them. And that's not exactly really fair to characterize them that way. And but I'll make that joke because I used to be one of those persons 3 years ago. I was in academia trying to use Google tools and a lot of open source geospatial tools. But nowadays I work with scientists like this. This is Tom Painter at the Jet Propulsion Laboratory, but he still kind of fits into that model because what he's holding in his hand here is a stick of dynamite. So these are the people I work with. They're passionate about environmental data. They spend a lot of time in the field. They're not necessarily IT professionals most of the time. They're scientists. They have scientific questions and problems. And my role is to be in between them. I come to conferences like this, go to AGU, EGU, scientific conferences, developer conferences, explain what Google's tools can do, and also, just as importantly, explain or find out what they can't do, and feed that back into the development at Google to try to improve Earth Engine in terms of expanding it for applications that we haven't really even thought about. Because the team within Earth Engine is rather small. We have people that came from like government research labs like NASA Ames, different universities like myself, University of Arizona, and then also core like Google computer scientists also. So it's a good mix, a small team, very passionate about trying to improve science and actually get rid of the barriers to getting science done. But a little bit more I want to give you a background of how I am familiar with California, or how I came to be here in California, and a background a little bit in water. The first time I came to California was in the 90s. Actually, I probably came out here skiing as a kid, but I was living in Colorado in the 90s at the time, going to Colorado State University, and came out to Sacramento to compete in the concrete canoe competition. And it was held on Folsom Lake, right here but near Sacramento. And it was a nice experience. I mean, you're here you've been studying all this stuff as an undergrad, not really applying much or something like that. This is an application of at least building something physical. I was in civil and environmental engineering, specializing in more like water aspects of the wet side of civil engineering, but also did, concrete design too. And so this is the first time that I came out to California and was exposed to it for any length of time. We did quite well. We got 5th place in there. After that, I took a bus ride down to LA because I had to go to another conference there, and I was a grad student, not flying around at that point. And I was staring out the bus, looking, as it goes down I-5, looking at the side of the road, and being amazed at this aqueduct. I mean, they don't have anything like that in Colorado. And then these penstocks moving water around. And I was reading Cadillac Desert at the time, getting really interested in what the politics and the physical mechanisms of moving water around in California is. And I took that bus ride down into LA because I was going to UCLA, and I learned a few things on that trip. Is one, don't take a bus to Los Angeles if you don't really know how to get to your endpoint because it drops you in Compton or Watts. 2, don't do it at night. It was dusk. So I was actually asking bus drivers, how do you get to UCLA? They had no idea. So that was one of the big adventures that I could go into detail over beers, but that was my introduction to California in some ways. I ended up coming back to California to do a master's degree at Caltech, and I had the fortunate opportunity to work with a PhD student at the time, Susan Paulson, who is now a professor at UCLA, and she was doing the study of water quality and mixing in the Sacramento Delta. So she was going out and doing grab samples, and she had some automated samplers that were out there and bringing some stuff back into the lab and doing a mass spectrometer to tease out the different signatures of the water. And I was responsible, as a summer student, basically a grad student working for her, is to put that in some type of database. So I started with Microsoft Access, and it's good for small data and at the time, and it actually has a kind of really nice graphical user interface. And for that small amount of data, it was great. And it was kind of eye-opening in my mind of learning what a database could be used for, because in my engineering undergrad and even through the master's at that point, none of that is taught really. But this is sort of like a practical tool, how do you start working with data? And I made some nice, charts for her and such, and then graduated and went on my way. And eventually, that ended up being part of publications that were put out, which I was happy to learn about years later. After that, I returned to Colorado, did environmental consulting for a while, but my job in Colorado sent me out to California, where I was working on Owens Dry Lake. And there I got to experience what happens when you take away the water that used to go to a lake bed. So we were out there trying to characterize a salt pile from a tungsten mine, and I spent many days out there putting in little wells into Owens Dry Lake, trying to measure what the piezometric head of the water is, which way the water is flowing. And what's interesting out there is it's bone dry. It's salt crystals that are hard to walk on. But there is water flow continuously. If you sit down on Owens Dry Lake, you get wet because it just evaporates so fast at the surface. But you would come back from a day of field work out there, and your pants they wouldn't bend. They would just be salt encrusted. I also learned another importance of water is that it prevents things from windstorms from wreaking havoc out there. Because if you're on Owens Dry Lake and the wind kicks up, which it did when I was doing field work there, you hide in a car or you hide in whatever you have available, like a wooden box, and try not to breathe the air. And as I said before, I was reading Cadillac Desert and relating myself to all the different politics going on at the time there. After that, I came back out to California again, went to school at Stanford, was studying civil and environmental engineering and doing groundwater and surface water, specifically spatial statistics. And at the time, I was doing a lot of analysis on groundwater, and I decided, this isn't really the thing. This is my future. This is the most excitement I could do in terms of field work, is going out, and seeing a well that didn't work or something like that, or a lot of water. So I wanted to switch to something else. I left California, went back to Colorado, and then this is my field work. It was actually starting to do characterization of snow in alpine basins, trying to figure out how you can use point measurements, because that's pretty much the best you have in many cases in snowy areas, whether it's in the Rocky Mountains or in California, and how do you extrapolate that over to large areas to answer questions of how much water are you going to have. And in the background here is Green Lakes Valley. It's actually the primary watershed for Boulder, Colorado, and so they're trying to predict how much water they will have in the reservoirs, and it's a hard problem. It's hard you learn a lot about data. You learn that there's data that you get given, and you don't really think about it when you're doing analysis, but when you're out in the field, there are those people, they have frozen fingers, they're trying to read something, it's blowing 50 miles an hour, and you have to realize that there is no such thing as ground truth data. There's just data that has various characteristics of uncertainty associated with it. So please, you can say ground reference data, don't say ground truth. That was one of the big lessons I learned there. This is another one of my sites that I was doing PhD research in. It was doing spatial variability with snowmelt, and this is a little more pleasant site. It was down below tree line. So that was my field work, and this is what it started looking like in Google Earth, which came out about that time. And this was a point of contention with my PhD advisor, because I started getting more interested in the tools than the actual science question in some way. And so he's like, so what's the science question? I'm like, I don't know, but we can share this, and we can do outreach, and we can do all kinds of things with all the data sets that are being collected there. So that started me down a path. After getting my PhD, I took a job as a research scientist at a university in Michigan, Michigan Tech University. And I started working with a lot of different technologies. Started off with a lot of the proprietary kind of software, scientific software, MATLAB, a little bit of ArcGIS, but I wasn't much of a user of that. But I started to develop a reputation for being able to win projects because I could apply cutting-edge geospatial software that is being released, whether it was proprietary or open source, to environmental problems. So I was trying to figure out how to put this talk together, not actually knowing so much about the audience that I was going to be talking to. And so I made a collection of deep thoughts, and here's my first one for the presentation here. I guess my first deep thought was actually about, taking the bus to LA. But deep thought number one for the presentation, at least, is Paul Ramsey changed my life too. I went to the 2007 free and open source software. I met Paul in a bar before the conference. That was my first introduction to a lot of the tools. I started, dabbling with it a little bit, but that really opened my eyes, that conference, of what this type of software can do. And for me, in the academic world, it was incredible because I could start working on a project and I didn't have a fear that I'd be stopped because of somebody else's fault. At least it was on me. I had the ability to go and fix what was wrong. I didn't have to report a bug and then wait a few years and see if it gets fixed, which doesn't really work. So if we back up here a little bit, you'll look in the background here, we have, Google Earth from Google here. It's displaying data that's formatted in a language called KML, which is an OGC standard, an open standard. And then over here on the left-hand side is the administrative panel for PostGIS, and I don't think it's up there, this might be, I can't tell whether it's fuzzy in there, and the other stuff I started using is Django, like a Python web framework. So started converting all of my work from being more of what I was taught in school or what was given me in school to what actually was really useful for solving these type of research problems. And for a research environment, the open source tools are awesome. So I started going to FOSS4G conferences, contributing to different pieces of software there, and writing software that other people would use too. All right, my second deep thought. I learned that environmental data is messy. I talked about a little bit this already. It always has uncertainties associated with it. There's gaps in the data. When you're dealing with remote sensing data, it's an indirect observation of everything. So there's always a model associated with those. Model has uncertainties. It's never really measuring what you want, or if you get a measurement that's precise enough to exactly what you want, you only have it for a limited spatial area. So you're always dealing with this wide variety of data sets, different characteristics, and so it's a question of how can you bring that all together? And it's not a question of whether the data is good or bad, it's just whether it is appropriate for the question that you're trying to ask to it. So it's good to focus on tools that allow you to bring out the best in data sets and multiple data sets, not just one. And then the next thought I had, and I only started to touch this when I was in grad school, it started to be more when I started working with remote sensing data. There's a lot of it out there. I mean, it's just the management of that data is really difficult, or it can be difficult. It can take all your time. So I'm going to talk a little about big data, and this means a lot of different things to a lot of different people. So here's my definition of big data. It's kind of meaningless at this point. Everybody has big data in some sense. It's just more data than you can handle. What I saw recently was the definition of medium data at a conference here, and I really like this one. It's basically it fits on a machine, but it's more than you can actually grasp in your head in some way. So that's medium data. That's a good goal to get your big data down to medium data. And then there's also small data. And this is basically something that you can graph. It could be an image, it could be a chart, it could be a yes or no answer. And so your goal with a lot of these big data problems is to how do you take your big data and move it to small data? And that might be a direct way to do that, or it might be getting it into medium data, and there's tons of tools that allow you to like deal with medium data. And Earth Engine deals with big data quite well. And we have tools to kind of get it to either one of these, to medium data or small data, depending on what question you're trying to answer. An example of big data that I deal with a lot is Landsat. And I don't know how familiar people would be with the Landsat program, but it is like an ongoing observation of the Earth's surface. It's been going on for over 40 years. The satellites have changed over that time, but it's basically nominally a 30-meter pixel size on the Earth's surface, about 7 bands of data. There's now being collected, I think the most recent sensor is collecting about 500, 600 images a day. Each of those images about a half a gigabyte. So if you have a new laptop, with a terabyte drive or something like that, it's on the order of a day or so if all you do is store the data and it's full. So it is a lot of data. A lot of it's probably being collected in parts of the world that you don't really care about, but in order to manage that amount of data, you have to stop thinking of like storing it on your own machine. It just doesn't work. It's also very messy. You have clouds, you have sun changes, you have sensor drift calibration over time. The sensor itself looks in different parts of the electromagnetic spectrum. That changes from sensor to sensor when you're combining 2 remote sensing instruments together. There's a lot of kind of scientific and physics knowledge that needs to be done in order to interpret that data. So what I have seen over the years is that in the idealized kind of like scientific hypothesis testing cycle, we'll have something that goes like this. We'll start off, create a hypothesis, and this might be like a professor saying, hey, I have this great idea that we can test about vegetation and how it's changing. And he talks to his grad students and says, go try that. All right, so then the grad student goes off and he's like, okay, he learns the discovery tools, the portals where he can maybe download the data. He finds it for an area that he thinks he might want to test. He figures out how to go through that web form and order the data and download it. If he's lucky, there's a bulk way to download it, but often there's not. And then he's trying to figure out how to put that into a place where you can start doing analysis on it. So this is a lot of like IT management too. Learn the software, put it in some place where you can actually start testing the problem, process the data. When I talk to people at like AGU, students and stuff at AGU and such, and show them Earth Engine, we'll show them something that we did in Earth Engine, and then they will say, that was the last 4 months of my life. And I'm just doing it as I'm talking with them in 5 minutes there. They get to the point where you can test the hypothesis, and then you go back to your professor and say, it might work based on what we've done. Do you want me to try doing some more? Do you want me to get some more data there? The cycle doesn't work very well for a lot of large data sets. The problem is sort of like I was talking about here, is that you start spending all your time in this management of the data. Download it, move it, analyze it. And your analysis here, the writing in the analysis program is, in a large part, not really the scientific analysis. It's like, how do you move the numbers around and how do you not overwhelm your machine? So a lot of time is wasted here. And scientists aren't the best IT people. There's a reason people go into science, and another reason they go into IT, and it's that Venn diagram of when you get both of them together, it's a really small amount of people that enjoy really both of those. But there are tools that are coming out that can help you take advantage of it. So you want to take advantage of all the data that is available, and the use of specialized tools can help you do that. And those are constantly evolving, but I think Earth Engine at least is one that's pretty exciting. So in Earth Engine, this cycle looks a little bit different. You still have the hypothesis creation here. Data discovery is more like a Google search at this point. It's just like, I want Landsat data, I want MODIS data. Type it in the search box, see what appears in Earth Engine. We basically load data sets as they're needed, so you're not going to find everything under the sun there. It's just what scientists have asked us for in the past. And then there is no ordering or downloading of data. It's just there. You can just reference it. So we're trying to get rid of, I don't know how many hundreds or thousands of times the same data has been downloaded over and over and put on somebody's machine, but we've done it once. We took the time and did it once. And then you write an analysis program. This tends to be a lot smaller because you're not focused on data management. You can process the data. We pride ourselves in doing things almost instantly or near instantly. We're pretty impatient people. So you usually get results back in the order of like 5 seconds or so if it's like a tough analysis. some are longer. And then you can test your hypothesis. And then you can, hopefully that doesn't take you very long to go around there. It might be, the initial run might be writing something, it takes an hour or something like that. I'm going to show you some examples later that I just asked some of the partners of Earth Engine to contribute for this talk, and I asked them like 2 days ago, and they started sending me stuff. So it doesn't really take a long time. It's not like a big part of their day. It's not an ongoing like commitment. It's like, it can be easy. So you can start doing the cycle fast, and we think that making the cycle fast will allow science to advance faster. So that's okay. That's the Earth at night, apparently. What we're showing here is some Landsat scenes from the Amazon. And over here is basically before deforestation. You can start seeing lines of it in deforestation, and eventually there's large lines there. I wanted to talk here about kind of the genesis of Earth Engine. It came because of Google Earth, and there were environmental groups that were using Google Earth and saying, if we just had access to that data that we see as the base map for like scientific purposes, we could do a lot with it. And they didn't need the high resolution data, they just wanted the free Landsat data. It was just in a way that was already put together. You can zoom to a different part of the world and just see it there. So that was the start. It's just like, how can we take a lot of the data that's at Google Earth and actually package it in a way that was useful for people that had real scientific questions about it. We have a lot of servers at Google. So if you think of it, YouTube itself, I think it's like 72 hours of video is loaded every minute. So there's like this multiplying factor. The total amount of like satellite remote sensing data is just small relative to like the camera video data, that people are taking YouTube videos. So we already have the infrastructure in place to handle this amount of data. It wasn't a big thing. It's basically we just had to build the tools for it. That's one of the great things about working, I would say, at Google, is coming from academia, is like the constraints, the resource constraints are just not there like you've had in the past in a large way. It's just you have different problems now. You still have problems. They're just different problems. They're not the resource constraints ones. Okay, so let's see if I can play this. This is going to be a little, if it works. This is actually, could you play that in the back? I did basically a recording of one of the interfaces of Earth Engine. It's showing you how, I'll walk through what's doing and then I'll explain what's going on. It's basically a user interface that I'm now loading up Landsat data. I'm going to take a percentile composite for an entire year. I didn't see exactly which year I was selecting. It's pulling all the Landsat data and mosaicing it to get a best pixel. We're in the Nile Delta area right now. And then I'm zooming in, and there's a few little guys here. These are training data that I put down to say, like, this is city and this is water. I have 4 different classes over here on the side: urban, vegetation, water, and desert. And then I'm having Earth Engine say, talk to a machine learning algorithm, a service. And it's going to take all of that training data that I specified, read in the Landsat data, send it off to this machine learning classifier, get back a model, and then it starts applying it to the Landsat data. So as fast as I'm panning around here, it just keeps applying that model. And if you could play that one more time here, I want to talk a little bit more about what's going on here. What you'll see as data starts coming in, it will come in chunks, like little blocks on the screen, and that's because we're distributing it over hundreds or thousands of computers at the time, and those computers are talking to their friends and things like that. So you can get kind of instant analysis back because we're chopping up the problem so finely that it becomes almost instantaneous to get the results back. At this point, there's not much of a algorithm that you can actually see. At the demo tonight, I will show you a lot more of the programming interface to it. There's so much control and so much control that you can have on Earth Engine in terms of what is being displayed. But that's kind of the philosophy of it. We want to have the results come back instantaneously, basically just where you're looking at, and as it pans around, it'll do more calculations. Once you get an algorithm you want, you can run it in batch mode for wherever the data is available, like globally if you want. And then you just have to worry about, like, where do you put it? You have to have a storage repository to, like, dump the data into. We make it very easy to share the data. There are tools up here that just say share your data, and it will just give you a URL that you can send off to your collaborator. They put it into a browser, and they get back the same analysis and the same point of the Earth. So if you have, like, something that's going wrong with your analysis, you can share that very easily. We make it as easy as just sending, like, a URL link to somebody else to share, as long as they have access to Earth Engine also. And if you can get me to the next slide. All right, so I'm going to show more static results, I guess, at this point of things that have been done with Earth Engine. This is one of those examples that I mentioned earlier that I just emailed some collaborators and said, what can you do in terms of providing me with some examples of use of Earth Engine? And this is from Justin Huntington and Charles Munson at the Desert Research Institute, and they basically implemented this paper, an algorithm that was in this paper by Rosenthal and Dozier on taking a Landsat thematic mapper and calculating where snow is. And this is the analysis for 2 separate years. 2010 is in yellow there, the snow extent in the Sierras from Landsat data, and then in red there, it's for this year, 2014, from Landsat 8 data. Once again, tonight I can show you that how it's done dynamically and the amount of code that goes into it. But the idea that they can just, within a day, just code up a paper and actually take what used to be, usually the end result of many of these scientific analysis is a journal publication. This is actually making it reusable, and you can build upon it for addition analysis quite easily. And that makes our scientists happy in general. Converting to happy scientists is what we're about in some ways. In my job, it's quite nice that I get a lot of feedback, weird feedback. I mean, sometimes it's direct to us, sometimes you just find it, like on Twitter or something like that. People that are just like, it blew my mind or something like that. And some are sad, yes, because it took them so long to do that before. But generally, there's been a lot of positive feedback on Earth Engine. What we're trying to capitalize on is a bunch of trends that are going on in IT, I guess, in general, and that is that bandwidth is getting cheaper per year. You're getting faster and faster internet connections, but it's kind of dwarfed by the drop in storage costs, and then even more so by the drop in CPU costs. And so that has a few key lessons that we're trying to take advantage of here. Is that the cheapest thing is CPU, and we expect that to become even cheaper in the future. So don't store stuff if you don't have to. Compute it on the fly, so we can minimize our storage costs. Just make use of all the CPU cycles you have. So a lot of the stuff that we display as products in Earth Engine isn't stored that way. It's generated on the fly. Algorithms are run. That includes even things like atmospheric correction, resampling, cloud detection. We can run those things on the fly. Disk is cheap too, so don't put your stuff on tape, bring it online. A lot of the data that we have in their Landsat, USGS has it on tape and they put it on their website. We basically mirror it and make it available to anybody that wants access to that Landsat data. And then, as I mentioned before here, CPU is cheap, so just don't pre-process, don't store additional copies, just do it on the fly if you can. My next deep thought is Barbara Ryan, in addition to Paul Ramsey, changed my life. Does anybody recognize that name? All right, we got one. Awesome. All right, she is currently the Geosecretariat Director, but the reason she changed my life is that she used to work at the USGS, and she was instrumental in the Landsat open data policy. And so if you look at this graph of the use of Landsat, starting back here in 2007 into 2008, they went from charging $600 per scene for distribution costs. It wasn't the cost for licensing the data, it was just the distribution cost, and you could share it as much as you want once you got it. But the use of it just took off. And this is amazing. I don't think they had any idea how well it was going to be used. It's starting to influence other groups around the world that have these large satellite programs. The Europeans, with their Copernicus Sentinel data, are speaking really great thoughts about free and open data. I hope that they go with a model that the USGS and NASA and government agencies have done with their open data. If that wouldn't have happened, I don't think there would be an Earth Engine. I don't think I'd be here today talking with you. It's just the ability to share data like that can generate so much economic activity, I think, in some ways. It's because it's free and open. We just got rid of that, or Barb got rid of that barrier here with, in conjunction with many other folks. Got rid of that barrier and made Landsat more useful because of the, freeing up the distribution costs, getting rid of that. But that's only the first step. I mean, it was made free, but now you have this problem of how do you deal with all that big data. So we are focused on the Earth Engine of going somewhat the next step is like make it, from a practical standpoint, make it usable. Not, you've got rid of the cost barrier right now, but there's many other barriers that are in the way there. So Earth Engine looks a little bit like this. It is servers that are sitting in Google data centers, and they know about geospatial data. They know about projections. They know about how to do things like reproject, and they are sitting in conjunction with a lot of data. So Landsat data, MODIS data. It's basically geospatial reference data is the data sets that we deal with here. And it can be public data, and that's mostly what I'm talking about here, but it also can be private data. We have security controls if you want to load up commercial imagery, and you can lock it down and people won't see it. But the stuff I'll be showing you is just generally the public data, which is the largest use of Earth Engine at this point. We also have a pool of algorithms, and these are things that can manipulate raster and vector data. It can add things together, it can join them, it can do buffering, it can do intersections, convolutions, things that you'd find in a GIS and remote sensing package. We have written algorithms within Earth Engine for those basic building block operations that scale across these thousands of computers. And so the job of the user of Earth Engine is to access Earth Engine through these APIs and construct algorithms that join together data sets with these algorithms. And it tends to be really short, generally. I mean, typically an algorithm is about 100 lines of code, half that being comments or something like that, because all you're doing is expressing what you want to do with the data, not how to manipulate, not how to manage it behind the scenes, but you just say, I want to add these two data sets together, or I want to take the median pixel value for an entire year, and that can be 1 or 2 lines of code. And so we're letting people focus more on the application or the algorithm development. And then on top of that, these APIs allow people to build applications. And so a lot of the stuff, that, especially the lightning talks today, were like, how do you make a web application? Earth Engine is really not focused on that. We're focused on if somebody is making a web application and they need data to like power it, the stuff that's going to be presented on the map. And how do you generate that on the fly? How do you do something interesting with remote sensing data? So that's our focus. This is some examples of the public data catalog of what we have in there right now. Landsat, as fast as USGS can get it off tape, we'll have it on there. We have over 3 million scenes on spinning disk. Many of the MODIS data products, terrain, different land cover products. We're starting to get into weather, atmospheric data. We're very much driven by our partners. They say, I have this interesting problem that I want to do, and it requires this data set and this algorithm, and if we don't have that, and it looks feasible to load it or write the algorithm, then we add to our collections like that. For Landsat, I mentioned earlier that we do also mirroring of the data that we download from like USGS, and this is sort of, in a way, it's a public service that we make it easier for people so they don't have to go through the web cart again to order a scene that's been ordered in the past. It doesn't have to be like pulled off of tape. We just mimic it here with a little link here that you can put in your whatever open, it could be a browser, or it could be a scripting language, and you can just download everything for a certain path row. We do that for many of the data sets if the user community wants that to do. Here's a brief history of Earth Engine. As I said, the reason Earth Engine, I think, came around is because of that open data policy, which was in 2008, and then 2009 is when Earth Engine started. So it started off with the idea of monitoring deforestation for developing world countries, but we made a very general platform and started moving up and up in terms of the larger and larger problems that we were trying to tackle. By the time we got to 2012, we were doing global analysis, global scale analysis, and we were also had that API that I was talking about. We have a developer environment with the API, made it a lot easier for our partners to work with. And some of the products I'm going to go through that came out in 2013 is this one. It's called Time Lapse, and it's basically from 1986 to 2012. It's a yearly snapshot of what, at a Landsat 30-meter scale, what the Earth looks like. And these are just 4 examples of it. The data set covers the entire world wherever there is Landsat data. So you can look at rivers migrating, you can look at cities growing, I guess that's also artificial cities growing, glaciers retreating and advancing, deforestation happening. It's just an incredible visualization of the data. It's just an RGB visualization, but you can actually learn so much of the world of just going around and looking at this. Because we've taken all the data that's available in the year and did our best to get rid of the clouds. So you're looking at, you're pretty much looking at the surface. And And we've kind of given that ability to some of our advanced scientists, or I should say that they have developed, gone way beyond what we did for time-lapse there. And some of the uses of Earth Engine that are pretty, to me, earth-shattering, I guess pun intended, is that this data set for Landsat 7, this is global forest change for the past 12 years. It was published in the Journal of Science. The lead author was Matt Hansen from the University of Maryland, and he took all of the available Landsat 7 data and figured out whether there was forest at 1 year and then it became non-forest, or the other way around, whether there's regrowth. It's available at a 30-meter resolution. It was published in Science. For the review process of this paper, the reviewers got to look at the entire world. We gave them an interactive viewer, so it's not just a figure in a publication. They got to play around with the data and investigate what Hansen was talking about in the paper. And then a few months later, this was released, the entire data set on Earth Engine or for download into a different system. We think this is a great use of Earth Engine, not just because it was groundbreaking in terms of the scale of what was done, but is also a good example of a scientist saying, go build upon this. I mean, I did all this work. I'm not going to hold it close and publish additional papers on it without letting anybody have access to it. You can just download it, or you can work with it in Earth Engine. One group that did take that data set and went with it is Global Forest Watch, or the application is Global Forest Watch by WIRI, the World Resource Institute, and they took that data set, the Hansen data set, and a few other algorithms from Earth Engine and a few data sources from elsewhere, and made this kind of public-facing website that allows you to track deforestation around the world by all these different algorithms. And you can actually now go in and say, hey, I want to monitor this area and get alerts when something happens. So if you care about a particular part of the world, you can use this interface in order to do that, and they on the back end are talking to Earth Engine and seeing if anything changed. Because there's different algorithms that are running. Some are running on a yearly scale, some are running on a monthly scale. We hope to get ones that are even quicker than that as new data arises. There's a lot of stuff that you can start doing when you if you stop thinking about remote sensing as just images that you're comparing, but you think of it as a sparse sampling of a continuous phenomenon. In this case, it is looking at, over the course of 40 years, the lights at night from a low resolution satellite. I think it was AVHR or DMSB. And you can fit trends to that. So you can start looking at, it's getting decreasing lights in this part of the United States, but then over here where there's a lot of development in Alberta, you're getting a red area, which means increase of lights at night. This is especially fascinating when you start looking at other countries. I mean, you got a lot of growth here in Mexico. When you go over to Europe, Poland is just off the charts in terms of its economic growth. Ukraine is the opposite. It's going the other way. So just being able to take these data sets and do really quick analysis like that, I find really exciting. Here's one that's more relevant to California. I wrote a script that looked at MODIS, calculated what's known as NDVI vegetation index, and then I compared this year to the corresponding previous decade, basically, since MODIS started, and look for an anomaly. And so in California, you see it's way below what it has been in the past. But the nice thing about the script is that you can just change the date, change where you're looking at the world, and see all kinds of droughts going on in different parts around the world too. There's signatures. We have a group that is from the University of Idaho, Desert Research Institute, and the University of Nebraska, and they're working on evapotranspiration modeling, so something that's really hard to measure itself. You have point measurements of it, but they're starting to get estimates of this from Landsat data on really large scales. It's basically the metric model is what they call it, and they're doing a port of this into Earth Engine. That's one I find quite exciting. Other things that our collaborators have been working on is a short-term drought index. So basically, given the current weather and a bunch of other inputs, Earth Engine is very good at combining different data sources together, both weather data, what you can see from remote sensing, and you don't have to worry about basically the projections and reformatting a lot of things that you would have to in another piece of software. But this is basically a measure of drought in some ways, a drought index. It's not just raster data, although most of our examples are from raster data, but we also have the ability to deal with point data, polygons and such, and sometimes that's clipping out the rasters, but we also have a lot of vector functionality that's written into Earth Engine too. We don't just have as much vector data to play with, I guess, at this point. Most of our public data set is raster. These are just a few of the groups that we've been working with. We work with individuals, researchers at universities. There's universities that have signed agreements for access to Earth Engine. I guess I should say that there's different ways of getting access to Earth Engine, because it's not something that Google sells. It's basically a technology, and we are giving it to a bunch of partners as they have a need for it, and it will become part of the commercial offerings of Google too. There's something called Maps Engine where you can actually store all your data, and when you purchase Maps Engine as a commercial entity, you can actually have access to Earth Engine, or we're starting to allow some of the users to have access to it, but as an experimental feature. But there's lots of groups that have been using it. They use it in operational scenarios. That just their operational scenario is kind of on different timescales. Like Amazon is doing monthly deforestation reports of the Amazon, and so every month they run analysis in Earth Engine to find areas that are likely deforested, and then they have an application built on top of Earth Engine where they go through and say, oh, this is and this is not, and they have like a manual kind of QA/QC to map where the new areas of deforestation is. It's stuff that's actually influencing government policy around the world, I would say. There's many other technologies at Google that are also useful for geospatial data. Cloud storage, I already showed you a little example of that. That's where all the Landsat data is just being dumped into it. It's basically a very large cloud-based file storage. There's Maps Engine, and that's a way that you can both upload your own private data for analysis in Earth Engine. So if it's not in the public data catalog, you can bring in your own data and assign who has access to it. You can keep it for yourself, or you can share it with others, or you can make it public. And then there's also publishing facilities within Maps Engine. So when Google crisis maps are displaying, data for Hurricane Sandy, that's what they're using. They're using Maps Engine. So it's basically a very large data distribution platform. We also have Compute Engine, which is just the ability to spin up your own Linux virtual machines. Just, if you need 100 or 1,000 for a short period of time, this is an awesome way to go for short-term analysis. And then Earth Engine can, they're all on the same data center, so it's very fast to transfer data between these different software packages at Google. We do take storage seriously, or security seriously for the data that is uploaded it, and we allow people to protect their data. It's very similar to how like Google Docs works, that you can assign permissions to a group or an individual, whether they have view access or download access, things like that. And then also there is a program for Google Maps Engine, which I mentioned, the way to load up your own data. If you want to load up your own data and make it public, then there's a way to get Google Maps Engine for free. So there's something that's called Google Maps Public Map Program. And at this point, it allows you to style your data into a map, and then you can upload that and share it with others. And then people can come and vote upon how well they like your map. Kind of the internet evaluation of what bubbles to the top is like what's the most interesting. So that might be useful for a lot of the data sets of different agencies. And it doesn't cost you anything other than the time, to upload the data. But in terms of licensing costs, then that's waived if it's made public data. So in my next deep thought that I'm back to, that it's only going to get more interesting in the future because there's some things that are coming along the way. This one I mentioned already is ESA has a Copernicus program that they are launching, aggressively launching satellites. The first one went up already. It's a SAR. There's going to be another one that's going to go up that's similar to Landsat called Sentinel-2, a coarse resolution imager. Another one that's going to be similar to MODIS. And then they're going to launch another SAR, another Landsat similar one, and then they're going to move on from there. It's going to be a total of like 10 satellites approximately in the next 5 to 10 years in there. They're estimating it's going to be 4 terabytes of data per day. We are loading a lot of data right now from Landsat, but it's only because there's this big backlog that Landsat's been around for a while. There's been a huge archive, and they just can't get it off tape. It's not generating terabytes of data per day, but for Copernicus, it's going to up the game again for the Sentinel satellite, the Sentinel series of satellites, that you're going to get terabytes a day of satellite data. Within California, there are startups that are looking at getting into the game of satellites. So actually, I should say they already have. Skybox Imaging, that's in Mountain View, they launched SkySat in 2013. They're going to put up eventually 24 of these. They're the size of a dorm fridge, and they cost a tenth as much as most of the other satellites that are up there. And they're hitching rides along with other satellites that are being launched. So they're not paying for their own launch vehicle or stuff like that. They're hitching a ride. They can keep their costs down, but they can get sub-meter imagery and video, which is kind of amazing when you look on their site. So video of a particular point, they'll just point at it and you get this 1 minute video of an area of interest. Another one is Planet Labs in San Francisco. They so far have launched 28 CubeSats, and they are the kind of a bread box size. And the interesting about this is that they have, the way that they're deploying is that they send them all to the International Space Station at once, and then they have basically astronauts chucking them out the lock every once in a while. And so to me, it's really interesting because my background in geostatistics is I love this irregular sampling. I mean, the idea of sampling things from different directions and stuff like that, it gives you more information if you know how to take advantage of it. They're planning another 100 in the next year that way, and they have, in this case, about 3 to 5 meter resolution, pointable. Another one that I'm pretty excited about is at JPL, NASA JPL in Pasadena. They are flying something called the Airborne Snow Observatory, and it's basically a LiDAR looking down at the snowpack of the Sierras. I can't remember whether it's once a week or once every other week that they're flying it, but they're getting really high resolution measurements of topography that's changing, the snow surface. So it's no longer like a couple of points out in these basins, the ones I was dealing with as a grad student. They're getting complete maps of snow depth and how it's changing over time. This is going to be incredible for water resource forecasting. So what's next for Earth Engine? Basically doing the same thing. And in some ways, we're expanding out to new domains, focusing more on water, disaster risk, climate change. Each of those new areas that we move into, our partners are going to ask for new data sets, new algorithms, so we basically keep adding to Earth Engine, expanding it in itself. We have this development cycle that is basically we have a new push pretty much every week is our goal there. Sometimes it doesn't happen for reasons, but it's on the weekly time scale, so you get new algorithms and new data sets pushed on a weekly cycle. So I know Paul earlier talked about the idea that you can't influence a commercial company. In this case, you can, because we don't have the 1 year lag and we're not selling updates or anything like that. It's just we're pushing it out as fast as we can. We're trying to forward in advanced science. We made an announcement a couple of months ago, the Climate Data Initiative, in terms of doing a lot of support for climate data resilience. And this is a web page from the White House. And our contribution or our commitment from Google is that we're going to donate a petabyte of storage for data sets that are related to climate change resilience. And that can be a lot of things. It can be additional satellite data. It can be weather, climate models for the future. It can be DEMs. And then we're also donating 50 million CPU hours of high-performance computing. That map that I showed you of the global forest change, 30 meters throughout the world for 12 years at a time, that's on the order of 1 to 2 million CPU hours. So we want to do another 25, 40 of those type of projects. And that's what we're stepping up and saying that we're just going to give that to scientists for free to do so. So that's Earth Engine. I'd be happy to demo more of this tonight, sticking around for the later session, and I can show you kind of on the fly what it does. But I hope that at least the presentation gave a good explanation of what it does too.